Thank you everyone for inviting me for this conference to give a talk. I'm Sivnandam. I'm from the University of Toronto. Today I'm going to talk about the Wide Integral Field Infrared Survey of nearby galaxies. Well, this is not yet an ongoing survey. It's going to happen very soon, and it's thanks to a new capability that we have, an instrument that we've been constructing for some time that will allow us to do this. And essentially, the punchline is we'll be able to follow up a lot of the current integral field surveys with our instrument. But before that, some context. So I would like to say that it is now currently the age of large integral field surveys. And there are two distinctions I wanted to make. Right now in the visible, there's certainly been an incredible proliferation of surveys of nearby galaxies. For example, just today we have the Khalifa final data release with almost 600 galaxies or 700 galaxies, and SABI and MANGA are ongoing, and they've really caused a significant utility increase for smaller telescopes and really allow us to drill down on the processes that drive the evolution of nearby galaxies. Whereas the infrared, things are a little bit different. The current instruments that exist are very narrow field spectrographs generally designed for very distant galaxies and high spatial resolution. And so there's obviously interesting surveys going on over there to understand the evolution and formation of galaxies at high redshift. And they generally go along with large telescopes so that you can get the high angular resolution and sensitivity that you need. Now, I'm going to argue that there's a space there that's not really fully utilized, where you could look at nearby galaxies, lower spatial resolution, and get much more interesting information that will complement a lot of optical surveys. So what do you get when you observe galaxies in the infrared rest frame? Well, so there's a very broad wavelength range, and one of the key things that you get from it is you basically look at the low mass stars and the evolved stars. So you get something that's a bit better mass weighted than light weighted in terms of the kind of stellar population that you look at. The other thing that you get is lower extinction, so you can look deeper into the galaxy and, for example, merging systems, etc. And of course, it's largely unexplored realm, partly because it's challenging to do in terms of observations. And so there's really a huge discovery space there. So just a little bit about the instrument capability that we've been constructing for the last few years. We're essentially building a near-infrared integral field spectrograph with a very wide field of view. Off the order of an arc minute by half an arc minute. Obviously, it's not very high spatial resolution, but it's comparable with existing optical IFUs out there, like that used for Khalifa and MANGA. And it's going to be on a 2-meter class telescope, and predominantly it's going to be very sensitive in this 0.9 to 1.35 micron range, where there's rich stellar spectral features. And we will also have some coverage over here, though it's slightly less sensitive. And of course, we also get very high spatial resolution because we're using lots of pixels underneath, spectral resolution, and so we should be able to do some kinematics. So just to give you a sense visually how much better we're doing, these are the common near-infrared integral field spectrographs that currently exist, the largest fields of view that you can possibly get from them. Obviously, they're higher angular resolution. And this is a nice nearby elliptical galaxy, so obviously it's not a very good match. This is the field of view of the spectrograph used for the Sauron and Atlas 3D surveys, so that gives you a sense of the scale. And Khalifa is by a factor of 2 larger than that. And this is the field of view that we will be able to attack. So it really shows you that it's well matched for nearby galaxies. Obviously, the question is when are we going to do this? in the next couple months, we're going to have the instrument on the telescope, just some pictures to prove that we're currently busily integrating and testing the instrument. Okay, so what kind of science are we going to do with this? And the main area that I'm going to focus on, obviously there are many other areas, is sort of the lowest hanging fruit, which is the stellar populations. Looking at stellar populations in the infrared. And there are predominantly two main questions that we're going to tackle with the survey that we're going to do, which is trying to measure the low mass end of the initial mass quantum. And because it's an integral field spectrograph, we can spatially resolve this and find correlations with other quantities. The other question is looking at the contribution of thermally pulsating AGB stars in post-Starburst galaxies to see what level of contribution they provide. Both of these questions are still debated as to what is really going on. And so for the one thing I wanted to highlight is that this is a nice result, stellar population, where everything is completely obvious what's happening. With the infrared data, we can really look at the red regions where you get the very low mass stars and the evolved stars, and for example, measure the dwarf to giant ratio to answer this question, and also look directly for these types of stars for the spectral features. Just to highlight that, this is an old plot that I found, but it's very illustrative of what's possible in the infrared. I have blocked out the infrared spectral region over here, and what you have here are different types of stars. So these are main sequence turnoff stars, and this is all the main sequence stars included. Red giant branch stars, asymptotic giant branch stars, and then low mass dwarfs, K and M dwarfs. And it gives you a sense of what are the dominant stellar components in the infrared wavelength range. This is for 3 gigayears, and this is an old plot, so that's the age of the universe back then. But it shows you that the evolved stars and the dwarfs start to have a significant signature, imprint on the infrared light. And so that's why it's a unique wavelength range where you can try to answer these types of questions. So obviously there's been quite a bit of debate about the low mass IMF in galaxies, with recent results stating that it's bottom heavy. And also there have been also conflicting results that from infrared studies and lensing measurements that suggest that no, it's not. And so our instrument will provide another regime where we can actually begin to test the stellar features that we would expect from low mass stars and giants. So here's something. This is the bandpass of the instrument. This is two models divided by each other: the bottom heavy model spectrum and the Milky Way spectrum, IMF spectrum. And you can see there are lots of spectral features that we can take advantage of that are either dwarf sensitive or giant sensitive. And to give you a sense of how long it will take, here's a simulated spectrum of a galaxy. The student who's here, Miranda Jarvis, wrote the simulator where we can actually provide the spatial, the illumination pattern and the spectra of galaxies, and figure out what signal-to-noise ratio we'll get in terms of spectra. So within 4 hours for a typical elliptical galaxy, we can get, by summing the spectra, the required signal-to-noise ratio to measure these types of features. The other contentious topic is the thermally pulsating AGB stars. There have been papers going back and forth saying they're important and not important. These are some relatively close by post-Starburst galaxies from this paper, where they have gotten spectra, relatively low resolution spectra in the infrared and optical, where they find that they can't fit the QPAGB heavy spectrum to it, and therefore conclude that it's not a significant contributor. And there are actually some very interesting features that our spectrograph can see. For example, there's this CN feature that we hope to attack with our survey. So what will this survey consist of? We've got about 50 nearby elliptical and spiral bulges and 10 post-starburst galaxies, and we'll be drawing them predominantly from Khalifa. And Khalifa is a great sample because it has a good match to the angular extent and spatial resolution of our spectra. Up here is a continuum image of an elliptical galaxy, and this is our field of view versus Khalifa. So with just two mappings of our field of view, we can actually get the same spatial coverage. So in the future, we hope to target manga galaxies, but first, for our initial survey, this is what we're trying to target. All right, so with this, I wanted to wrap up and just talk about some additional directions that we can go. I mean, it's really rich in all the things that we can potentially do. For example, there are some interesting projects in high mass star formation. There are some features like helium emission and fashion beta to understand what the fraction of high mass stars are in a star forming region. Because we're not very sensitive to extinction, we can look at star formation in emerging systems. We can also look at dust distribution in galaxies. Khalifa or other nearby galaxy surveys have H alpha. We can get fashion beta and get a very good estimate of dust distribution. There are some very interesting kinematics questions that we can answer. Merging galaxies is very interesting. Looking for pseudobulges, and also looking at active galactic nuclei, for example, in Seyfert galaxies. So these are all enabled by these interesting advantages of near-Earth spectroscopy. So of course, one of the reasons I'm here is that I can talk to you guys and get new ideas, so please come and talk to me, and if you have some interesting ideas to do with this new capability. Thank you very much.
Okay, so who wants to buy into Wi-Fi? Kevin?
Wi-Fi.
Wi-Fi, yeah.
And then I know that there's wives in Australia.
Right.
Can you say anything about your strategies for skies and country?
Yes, that's a very, very good question. So we have a couple things that we're going to do with that. And one of I think the bigger problem is the telluric correction. And so what we have is we actually have a separate imager on the instrument that looks in the Z-band that we will continuously get data on a particular star to see how the telluric absorption is changing, so that we can scale it appropriately when we do the correction later. And because we have full control of the observing strategy, so we'll have the opportunity to increase the number of standards that we observe. And this is not a fiber-based IFU, so it's a slicer. So it's a little bit easier to do those types of corrections than, for example, sky subtraction.
Other question? Martin Bureau in the back.
Oh, one other thing I should mention, we have a small Gemini NIPS program to get a better understanding on this in terms of sky subtraction and telluric correction. So we have some data that we're working with.
Great instrument. Thank you very much. Now, of course, the question is that going to be operated as a private user instrument, or is it going to be open by on it?
So right now it's a collaborative endeavor with the University of Arizona. So it's right now in a closed collaboration. However, I think we're definitely open to collaborators that would be part of that larger collaboration.
One or two more questions? Well, as you said, you're inviting people to come talk to you, so hopefully we will all do that. Thank you very much, Suresh.